Hi everyone, today we will learn about the switching characteristics of MOSFET. In that we will learn about switch concepts, design of the circuit, its waveform and testing of the circuit. So what is a switch? One simple switch I will draw here. This is a ground point and this is supply point. So what will happen when the switch is in the closed position? And what will happen when the switch is in the open position? Switch is closed, what will happen? Switch is open, what will happen? Close means switch is in the on condition. Open means switch is in the off condition. So we are dealing with the output current and voltage. So when the switch is in the open position, there is no current flow. It is open. There is no current flow. There is no connection and there is no current flow when the switch is in the open. That is, it is approximately, current is approximately equal to 0. And what about the voltage? Voltage across the switch. So voltage across the switch will be maximum. That means the switch is open. So when we are connecting the multimeter probe across this switch, one point is this and other one is this. This is ground and this is VDD. So this high voltage will be getting as the reading. So voltage will be maximum, or we can write it as VDD. It will be almost equivalent to supply voltage. When we are closing the switch, what will happen? There will be a current flow. The switch is closed, current flow will be there. Current will start flowing. So current we are measuring in series with the circuit. Ammeter will be connecting in series and voltmeter will be connecting in parallel. So current flow will be there. So there will be a maximum current flow. And what will happen to voltage? Voltage across the switch, that is minimum. That means the switch is connected to ground. So there will be minimal voltage drop across the switch. Voltage across the switch will be minimum. This is the basic switch concept we should know. What will happen when the switch is in open position and closed position? Open means current 0 and voltage maximum. Closed means current maximum and voltage will be minimum. Here we are learning about MOSFET circuit. So how the MOSFET is acting as a switch. So when we are drawing the diagram of a switch or when we are using a switch, the required quality should be its fastness, or it should operate in high frequency. It should be when you are turning on, suddenly you should get the output. There should not be any delay. So why this delay is coming in the case of MOSFET? Almost all switches will be having delays. In the case of MOSFET, the delay is coming mainly because of inter-electrode capacitance. Because of this capacitance effect, delay is coming. If you're taking the example of BJT transistor, their delay is coming because of parasitic capacitance. And MOSFET, it is inter-electrode capacitance. So what is inter-electrode capacitance? Suppose you are taking, this is gate connection, drain and source. In between gate and drain, one capacitance effect is there. In between gate and source also capacitance effect is there. Between drain and source also capacitance effect is there. So when we want to turn on the device, this capacitance effect will hinder the delay. There will be delay projected by this capacitance. While offing also same thing will happen. That recurs the charging and discharging of this capacitance. So because of this inter-electrode capacitance, the delay is coming in the case of MOSFET. So here we will draw the circuit. So in the drain, I'll be connecting a resistor as load. And gate, also one resistor is required for limiting the current to gate. And a supply is required to a pulse of some frequency is required at the gate. And this can be named as RG, gate resistance. And here one more resistance is required, that is RGTH. This is actually for grounding the capacitance effect. There is a chance the MOSFET can accidentally turn on without the gate supply. So for avoiding that, we are keeping this RGTH for avoiding the accidental turn on of the MOSFET. This is the load or drain resistance RD. Here, for example, we can give voltage of 10 volt VDD, and this is VSS. Here some frequency we need to give, for example, 10 kilohertz, and duty cycle 60% I am giving here. So this is a circuit diagram for switching. We need to measure the current and voltage, that later we will tell. First we will design all these components. So RD we need to design this resistance. RG we need to design RGTH. And MOSFET here I am taking IR of 640. So 3 resistance we need to design. For designing the resistance value, we can simply use Ohm's law. That is V equals IR. So R value we need to find means R will be equal to V by I. So for find here RD by ID, that is 10 volt by 1 amps, that will be equal to 10 ohms. And we need to find the power dissipation, that is V into I, VD into ID, that is 10 volt into 1 amps, that will be 10 watt. So we need to choose a resistor RD. The value will be 10 ohm, 10 watt. Next, we will design RG. So RG means the voltage across this resistor by IG. That is voltage across this resistor means we need to find the potential difference. So what is the input voltage minus what is the gate voltage? So for turning on the MOSFET, minimum threshold voltage it is 4 volt. Typically, it is from 2 to 3. Here I am taking 4 volt. We can check the data sheet. Gate threshold voltage, typical value, it is from 2 to 2 minimum, 3 typical, and 4 maximum. So I'm taking this maximum value 4 volt. So V input minus threshold voltage by current IG plus. This current we need to find. We don't know the current. We input here 10 volt peak to peak pulse I am giving. So that is 10 volt minus threshold voltage from data sheet, it is 4 volt by IG plus. So here how we can find IG plus? So for finding IG plus, we need to find IG, gate current. Gate current, we can find out from the equation, charge is equal to I into T. Charge will be equal to current into time T. So here From this equation, we can change it and we can take it as this current can be written as I is equal to Q by T, or Ig can be written as gate charge divided by T on. So two parameters are there, Qg and T on. We need to find Qg from data sheet, and T on we can find from this frequency. So first we will find Qg from data sheet. So here data sheet it is written, total charge it is 63 nano coulombs. So we can substitute it there. Qg is 63 nano coulombs by T on. So how we can find T on? Frequency is given as 10 kilohertz. And duty cycle is given as 60%. So time period will be equal to 1 by frequency, that is 1 by 10 kilohertz. That can be written as 1 by 10 kilohertz means 0.1 milliseconds or 100 microseconds. So what is T on? T on is equal to duty cycle into total time period. Here duty cycle is 60%, that means 0.6. I'm taking out the percentage divided by 100. So 60% will be equal to 0.6. So 0.6 into total time period is 100 microseconds. We'll be getting the answer as 60 microseconds. So your T on is 60 microseconds. So Ig we can find it. Ig equal to Qg by T on. Qg is taken from data sheet and T on is 60 microseconds. So calculate the value. 60 nanocoulombs by 63 nanocoulombs by 60 microseconds. That's equal to 0.95 into nano means 10 raised to minus 9. Micro means it is 10 raised to minus 6. When it is going top, it will be plus 6. So the answer will be 0.95 into 10 raised to minus 3 amps, or we can write it as 0.95 milliamps. Actually, this current is very less to drive the gate. So we need to calculate Ig plus that will be equal to 2 into Ig. So that is 2 times our calculated value we need to take for the driving the MOSFET. So the answer is 2 into 0.95, that is 1.9 milliamps. So we can find Rg. So Rg is equal to 10 minus 4 volt, that is 6 volt by 1.9 milliamps. So this was Rg equation. 10 minus 4, Ig plus is there. So we are substitute the value. This will be equal to 3 point. This milli will go on the top, 10 raised to minus 3 will go on the top and will become 10 raised to plus 3, that is kilo. So 3.1 kilo ohm. Next we need to find RGTH. So this is RGTH. For avoiding the inter-electrode capacitance effect, we are putting this RGTH. Or we can tell to avoid the accidental turn on of the MOSFET. MOSFET should not turn on accidentally. So for avoiding the accidental turn on of the MOSFET, we are putting RGTH. We need to avoid the capacitance effect. So always the RGTH value should be higher. That is, we will take it as 10 times Rg. So 10 into 3.1 K We'll be getting the answer as 31 kilo ohm. So now the design is over. Three values we have got. That is RD value is 10 ohm, 10 watt. RG value is 3.1 kilo ohm. And RGTH, it is 31 kilo ohm. We can find the power rating also by multiplying these two values. It will be within half watt. Next, we will see the waveforms. So how we will draw the waveforms? So we need to draw the gate input voltage. What is the voltage across gate and source? Across gate and source, how the voltage will be. And across drain and source, if you want, we can draw. And what is the current through the load? While drawing the waveform, we need to plot V input, VGS, ID, drain current, and VDS with respect to time. So this is your input voltage. I'm taking T on. This portion will be T off. So during T on condition, what will happen? When T on is given, your MOSFET will be getting on. Before you have seen, threshold voltage is 4 volt. So after 4 volt, the switch will be closed. MOSFET is getting in the on condition. So first we will plot this VGS. Then current ID. So once it is in the on condition, current ID will be there. ID will start increasing. And your VDS will start decreasing. We are just plotting T on only. So on condition, switch is closed, ID will increase, the voltage through the switch will increase, and voltage across the switch will start decreasing. And VGS will be there. After 4 volt, it will get in the on condition. So for drawing this waveform, I have marked 3 dotted lines. This T on position and T off position, 3 dotted lines I have drawn. So first I am drawing this VGS. So when you're giving input, after 4 volt, your VGS, that is MOSFET is getting on. Here some bend will be there. Like this, the wave will go. When you're doing it practically, we can see this bend. So this bend can be marked as VT, your threshold voltage. And this point, this is 90%. So this point can be marked as VP, threshold voltage. We are told before that after VP, the current will be remaining constant. That is a pinch of voltage. Then a straight line. Then from here to this bend, again, it will come to 0. This will be the waveform that we can observe in CRO. Then what about ID current? So when T on is given, ID will be there. So from here to 10% rise, from that point to 90% rise. So we'll tell what is this 10% and what is this 90%. This is 10% and this point is 90%. This I'm extending here also around 10% point. This will be 90% point. So after pinch off, the current is constant. And at this point, T on is coming to 0 position. So because of the inter-electrode capacitance, still your MOSFET will be on. Some current will be there. This is from maximum to 90%. And from 90 to, sorry, this is almost a straight line. Here, there will not be any bend. Here the current will start reducing from this maximum to 90%, 90 to 10%. And here the voltage waveform will be just opposite of the current. Before you had told that when your switch is in the closed position, your current will increase and voltage will decrease. It is just inverse. That is across the switch voltage and through the switch current. So in this graph, when current is rising, the voltage will be falling. And here we will deal with the timings. That means when you're given input, the current will start rising from 0 to 10% rise. Or the voltage VGS from this minimum to VT threshold voltage. That is, at that point of time, it will start conducting. So this 0 to 10% of time, that is called as TDN. And this 10% to 90%, that rise is called as TR. The rise of current from 10% to 90% of the maximum ID current. This is your maximum ID current. So 10% to 90% of the maximum ID current is your rise time TR. So here two types of delay is coming. T on delay and T off delay. Before we are told the total delay that is coming in the MOSFET is due to inter-electrode capacitance. So here total delay will be equal to T on delay plus T off delay. And T on delay is occurring during T on time. When your MOSFET is getting on, we are giving an on pulse, that delay will occur and that will be equal to TDN, that is 0 to 10% rise, plus TR, that is 10% to 90% rise. So T on delay is equal to TDN plus TR. And when you are giving the T off, from this point it is T off. So T off is given means the voltage across the gate will start reducing. That means the current will start falling. So from this maximum point to 90% fall, that is called as TDF or turn off delay, TDF. And again the current will fall from 90% to 10%. This fall is called as TF or fall time. So T off delay is equal to TDF plus TF fall time. And this is the total delay, that is T on delay plus T off delay. And we can check the data sheet for the values. Here TD on, turn on delay time is given. These were the particular condition given here. That is 12 nanoseconds. Rise time is 45 nanoseconds. T off delay, TDF is 54 nanoseconds and TF fall time is 38 nanoseconds. So according to this condition given, we have got the answer. We can compare the same thing. Now we'll deal with the checkpoints. That means once you have connected the circuit, we will be having some trouble in getting output. So how we can check the circuit? What are the important things we should keep in mind for checking the circuit? First is, before connecting, we need to check the MOSFET, whether the MOSFET is working or not. So how we can check the MOSFET? MOSFET IR of 640, it will be having three terminals, that is gate, drain and source, GDS. So for checking this one, first we will be checking the resistance across drain and source without applying any voltage to gate. That is the first point. And it should show in mega ohm range. The resistance should be in mega ohm across drain and source. Again, we can check by applying a positive 4 volt. It is an N channel. We are taking IR of 640. It is N channel MOSFET. So you can apply a positive voltage to gate in the second condition. Again, check the resistance. It should come in ohm range. Some 10 ohm or 2 ohm, 3 ohm. In that range, it is coming. So we can confirm that your MOSFET is in working condition. Next thing, you can check the power supply. So we have designed the circuit for around 1 amp. So the power supply's current knob should be in maximum range. Current knob, you can see it should be in maximum range. Normally in labs, you are using sometimes 1 amp power supplies or 2 amps. Maximum 2 amps you'll be using. So keep that one in the maximum position. Then only we'll get output. Then remaining things are our normal checkup. That is, we need to check the probes, CRO channels, check the channels. Then breadboard connections we can see. So once you connect the circuit, these are the common things every time we'll check. The main thing here is MOSFET is working or the power supply current knob should be in maximum position. Then our frequency setting, it should be correct. Otherwise it will not work. Frequency and duty cycle setting should be correct. Once you connect the circuit, if everything is okay, first we'll check the VGS. If you are getting this bent voltage, some slight bend will be there. Then you'll surely get the output. Your circuit is in the working condition. Hope you got the switching cara of MOSFET. Its design, how we can design the circuit with the help of data sheet, and what is the waveforms, and how we can check the circuit, minimum checking of the circuit. So thank you all. We will see in the next video. Bye.